This is Lesson 8 in our Calculus 1 series, the derivative at a point. In this lesson, we're really starting to talk about calculus. Lessons 1 through 7 were really a review of pre-calculus topics. But now we're beginning to talk about the rate of change of a function, and that's really what calculus is about. So we're interested in finding the rate of change of a function y equals f of x at a point, say, x equals a. And so we're talking about here the change in f with respect to a change in x at the point x equals a. So we're talking about a rate of change here, and so it sounds like we're looking for the slope of f of x. And that's exactly what we're looking for. We say the slope of f of x at x equals a is equal to the slope of the tangent line to f of x at x equals a. And so the tangent line to f of x at x equals a is the line touching the graph of y equals f of x at the point x equals a with the same direction as the function at that point. So we can think of zooming in on the graph of y equals f of x at the point where x is equal to a. And so for this function f of x at this point x equals a, we're talking about this blue line here that is touching at the point x equals a and going in the same direction as the function. So when we talk about the slope of the function at this point, we're talking about the slope of the tangent line at this point. And so some other examples here. In this case, the tangent line is not just touching at a point, but it's intersecting the curve, and that's perfectly okay. And here we notice we have a horizontal tangent line at x equals a. So to find the slope of the function y equals f of x at x equals a, we find the slope of the tangent line to the function at that point. But we only know how to find the slope of a line for which we know 2 points. And here, the only information we're starting out with is 1 point, the point of tangency, a, f of a, and the function's formula. We know y equals f of x. We'll have this function formula. So we need to figure out how to find the slope of the tangent line with the given information. So let's consider this parabola. F of x equals negative x minus 2 squared plus 2. And I wrote it in this form so that it's easy for us to think about the graph. So think about your function transformations. We're starting with our basic parabola. We're moving it to the right 2 units. Then we're turning it upside down with this negative sign. And then we're shifting it up 2 units. So this is what our parabola looks like. And we're going to talk about finding the slope at x equals 1. So at x equals 1, the function value here is 1, so we're looking for the slope here at 1, 1. And so that's the slope of the tangent line to the graph at 1, 1. Now again, we said we don't have any methods for finding the slope of a line without having 2 points on that line. So let's use that idea to get at least an approximation to this tangent line slope. Let's take a look at the secant line between the points 1, 1 and 2, 2. Notice that 2, 2 is another point on our function. It's on our parabola. And we're looking at the secant line. That's the line that goes through the curve through those 2 points. And let's take its slope as an approximation to the tangent line slope that we're looking for. So this slope is going to be 2 minus 1 over 2 minus 1, so that slope is equal to 1. And so this is an approximation to the red tangent line slope that we're looking for. But it's not a very good approximation. So let's try to get a little bit closer of an approximation by, instead of using the point where x is equal to 2 on our parabola, let's let x equal maybe 1.5. So now this slope we can see just from the picture is going to be a better approximation to the slope that we're looking for. And we notice here when x is equal to 1.5, our corresponding function value f of x is equal to 1.75. We plug that into our function, we get 1.75. And if we take the slope of this secant line, this green line here, we get 1.5. Right, we have y2 minus y1 over x2 minus x1. And so that gives us 1.5, 1.5. And so that's a better approximation, but it's still not close enough. So we notice that really what we're looking for with the slope of the tangent line is the limit of these secant slopes as the second point gets closer to our point 1, 1. So the slope of the tangent line is equal to the limit of the slopes of the secant line as the x value of the second point gets closer to 1. So as we move that second point in closer to x equals 1. So let's take a look at the general notation. Here's our point A, f of A, and here's our second point that we're using for the secant line, and this we're going to call A plus h, comma, f of A plus h. So we're saying from point A, move over h units, and now we're looking at the x value A plus h, and its corresponding function value on the parabola. And so these are the 2 points that we're going to use for our secant slope. So the slope of the secant line here is f of A plus h minus f of A. It's y2 minus y1 over A plus h minus A. A plus h minus A. And so that simplifies to f of A plus h minus f of A over h. And what we said is that the tangent line slope that we're looking for is going to be the limit of these secant slopes as h goes to 0. So the slope of the tangent line to f of x at x equals a is the limit as h goes to 0 of the secant slope, f of a plus h minus f of a over h. So for our example, let's compute the slope of the tangent line. The parabola we have is f of x equals negative x minus 2 squared plus 2. And so if we just multiply that out and simplify, that's going to be negative x squared plus 4x minus 2. And we're looking at the point where x is equal to 1. So the slope of the tangent line to f of x at x equals 1 is going to be, we're plugging a 1 in for a here. So we have limit as h goes to 0, f of 1 plus h minus f of 1 over h. And so f of 1 plus h is going to be negative 1 plus h squared plus 4, 1 plus h minus 2. So that's negative 1 plus h squared plus 4 quantity 1 plus h minus 2. And then minus f of 1 is equal to negative 1 plus 4 minus 2, so that's a 1. So f of 1 is equal to 1, and that gets subtracted here. And this is all over h. Now, if we try to just plug in h equals 0 here, what's going to happen? We're going to end up with 0 over 0. So that's not going to be helpful. That's an indeterminate form, and it means we need more information. So our process here is always going to be to perform some mathematical manipulation on the expression to get an h to cancel from the numerator and the denominator. And then, once we do that, we can plug in h equals 0. So here, what we need to do is just expand and simplify our numerator. So we multiply through this 1 plus h squared. We distribute that negative sign. And we simplify our numerator. We notice that we have a negative 1, a negative 3, and a positive 4. That all cancels. And we have a negative 2h and a positive 4h. So that gives us a positive 2h. And the minus h squared carries as well. So now we have the limit as h goes to 0 of 2h minus h squared over h. And this looks great because we can see that every term in our numerator has a factor of h. So we can go ahead and factor that out and cancel it with the h in the denominator. Now at this point, since we've canceled the h, we're left with limit as h goes to 0, 2 minus h. We can just plug in h equals 0. And so we get a slope of 2. This is the slope of the tangent line to the graph at x equals 1. So this is what we just found. This slope is equal to 2. So we just found the slope of this tangent line, and it's very common to ask after that, well, what's the equation of that tangent line? So I'd like you to please pause the video and work out the equation of that tangent line. Well, we know that the equation of a line can be written as y equals mx plus b in slope-intercept form, or in point-slope form, that looks like y minus y1 equals mx minus x1. And we're given the point 1, 1, that's the point of tangency, and we found that the slope m is equal to 2. So using point-slope form, it looks like y minus 1 is equal to 2x minus 1, and simplifying, we get y equals 2x minus 1. Or if you're more comfortable with slope-intercept form, you can plug in your y and your x values, plug in your slope m to solve for b, and you get b equals -1, and we get, of course, the same line. Y equals 2x minus 1. That's the equation of the tangent line to this curve at x equals 1. And it's very common to ask for the equation of the tangent line, not just the slope. So you should be prepared to see that often. Now, I just want to point out, we used the secant slope approximations above to develop the idea of using the limit to get the slope of the tangent line. But for future computations, we're going to go straight to the limit computation. I also want to point out, we use the limit here in this notation, limit as h goes to 0 of f of a plus h minus f of a over a plus h minus a, which simplified here. And this is the slope of the secant line through the points a, f of a, and a plus h, f of a plus h. And here we let h go to 0. But we could write this in different notation. We could also use the notation limit as x goes to a of f of x minus f of a over x minus a. So what we're saying is that our second point is called x f of x. And we let x approach a. And so this is the slope of the secant line through a f of a and x f of x. It's just a different way of noting that second point. And so our limit looks a little bit different, but it also gives the same result. It gives the slope of the tangent line to f of x at x equals a. So we have two formulas that we can use, and we're going to talk a little bit more about them in another minute or so. But first I want to mention that these computations are called the derivative of f at x equals a. And we denote this by writing f prime of a. So what we're saying is that all of these mean the same thing. F prime of a is the limit as h goes to 0 of f of a plus h minus f of a over h. We could also use instead this limit, limit as x goes to a, f of x minus f of a over x minus a. And these both represent the slope of f of x at x equals a, which is also the slope of the tangent line to f of x at x equals a. And this is called the derivative of f at x equals a. And by the end of the lesson, we're also going to see we can call this the instantaneous rate of change of f at x equals a. So we have all of these expressions that mean the same thing, and you really need to get comfortable using these expressions interchangeably. We could ask you for the slope of the function at a point, we could ask you for the derivative of f at a point, we could ask you for the instantaneous rate of change of f at a point, and you need to know that they're all the same computation. So now let's take a closer look at comparing these two formulas. The first one we looked at takes limit as h go to 0, f of a plus h minus f of a over h. We're using the 2 points a f of a and a plus h, f of a plus h. And we let h go to 0, that brings this second point closer in to the first. And so we get in the limit the slope of the tangent line. This computation is usually going to be more convenient for you. But we could also see this other notation where we're calling the second point x f of x. And then with this notation, the slope looks like this, f of x minus f of a over x minus a. And then in the limit, we're saying x approaches a. X approaches a. So this computation gives us exactly the same result. It's just written in a different form. And so it might be more convenient for a few cases, and in my opinion, it's only most convenient for f of x with high powers. for which f of a plus h would be messy. So, for example, if we're looking at f of x equals x to the fifth and we want to find f prime of 2, if we set up our original computation, limit as h goes to 0, f of 2 plus h minus f of 2 over h, that means we have to expand 2 plus h to the fifth power. It's messy to multiply out and it leaves a lot of room for error. So instead, we could take a look at this other form of the formula. Limit as x goes to 2, f of x minus f of 2 over x minus 2. And so this says we're looking at limit as x goes to 2 of x to the fifth minus 2 to the fifth over x minus 2. So instead of trying to manipulate it so that we have an h over h to cancel, here what we're trying to do is get a factor of x minus 2 in the numerator so that we can cancel the x minus 2's. So we have to take this numerator and factor out an x minus 2. And so for that factoring, I like to use long division, but you can certainly use synthetic division if you're more comfortable with that. So let's take a look at the long division here so that we can factor, this is x to the fifth minus 32. Let's factor an x minus 2 from that. So the first thing I'm going to do is write out my x to the fifth minus 32, but I'm going to leave spaces for the x to the fourth, x to the third, x squared, and x terms. And I've got my x minus 2 on the outside here for the division. And so the question is, how many times does x minus 2 go into x to the fifth? Well, I would need to multiply by x to the fourth to get an x to the fifth here. So I'm going to put 1 x to the fourth, and I'm going to multiply that through. And that's going to give me x to the fifth minus 2 x to the fourth. And so I subtract, and that gives me a 0 here, and a positive 2 x to the fourth here. And I bring down nothing here because I have a 0 x to the third. And now I want to know how many times does x minus 2 go into 2 x to the fourth? In other words, what would I have to multiply x minus 2 by to get a 2 x to the fourth? Well, I would need a 2 x to the third. And I'm going to write that above the x to the third term here. So 2x to the third times x minus 2 gives us 2x to the fourth minus 4x to the third. And so subtracting here gives us 0 here, and then a positive 4x to the third here. Again, we bring down nothing, and now we want to know what do we need to multiply x minus 2 by to get a 4x to the third. And that's going to be a 4x squared. So 4x squared times x minus 2 is going to be 4x to the third minus 8x squared. And again, we subtract, and so that becomes 0, and here we have a positive 8x squared. We bring down nothing again in the x term, and how many times does x minus 2 go into 8x squared? We need to multiply by an 8x. 8x times x minus 2 is 8x squared minus 16x. So we subtract, and we get a positive 16x here. Now we can bring down our negative 32, and we have x minus 2 goes into 16x minus 32 16 times. So we have a positive 16 here. And this becomes 16x minus 32, and we subtract, and we get a 0. So that's how we get the factoring here. We have x to the fifth minus 32 can factor as x minus 2 times x to the fourth plus 2x to the third plus 4x squared plus 8x plus 16. And so that goes here. And now that we have this factoring, we can cancel our x minus 2 factors. So we're taking the limit as x goes to 2 of x to the fourth plus 2x to the third plus 4x squared plus 8x plus 16. And so we can just plug in x equals 2, and that gives us 80. And so 80 is equal to f prime of 2. And so again, in this case, because we had a high power of x, it was more convenient to use this formula than it was to use limit as h goes to 0. But generally speaking, it's going to be much more convenient to use the original formula with limit h going to 0. So let's take a look at another example. Find the slope of f of x equals radical x plus 1 at x equals 3. So we know that the slope of f of x at x equals 3 is equal to the slope of the tangent line to the function at that point, and that's the derivative of f at 3, so that's f prime of 3, and so we set up our limit definition here. Limit as h goes to 0, f of 3 plus h minus f of 3 over h. And so f of 3 plus h means we plug in a 3 plus h here, and so we have radical 3 plus h plus 1 minus f of 3, so that's radical 3 plus 1 all over h. And simplifying, our numerator looks like this. We have radical 4 plus h minus 2 over h. But in order to be able to factor and cancel an h, we're going to have to get this h out of the radical sign, which means we are going to have to multiply by the conjugate here, so that's going to be radical 4 plus h plus 2 over itself. And again, the conjugate means this negative turns to a positive. And when we distribute here, we multiply through the numerators, we're going to get a 4 plus h from the first terms. The inside and outside terms cancel, and we get a negative 4. So we're here. And we notice we have a positive 4 and a negative 4, so that cancels additively. And then we're left with h over h times radical 4 plus h plus 2. And so these h's cancel. And now we can plug in h equals 0. And so we get 1 over radical 4 plus 2, and that's 1/4. And so this is the slope of this curve at x equals 3. Let's take a look at another example. Find an equation of the tangent line to g of x equals 2x plus 1 over x plus 3 at x equals 2. So in order to find an equation of the tangent line, we need the slope of the tangent line and a point on that line. Well, we're given x equals 2 for the point of tangency, so we just need to find g of 2 for the corresponding y value for that point. So plugging 2 in here, we see we get 5 over 5, and that's equal to 1. So we have g of 2 is equal to 1, and so the point of tangency is 2, 1. Now we need the slope of the tangent line, and so that's going to be g prime of 2. So we're going to set up our limit as h goes to 0 of g of 2 plus h minus g of 2 over h. So our function g of x is 2x plus 1 over x plus 3, so we're plugging in 2 plus h for x. So we have 2 times 2 plus h plus 1 in the numerator and 2 plus h plus 3 in the denominator. And this is minus g of 2, which we evaluated as 1, all over h. So simplifying our first fraction here, we have 4 plus 2h plus 1 over 5 plus h. And continuing to simplify, that's 5 plus 2h over 5 plus h. Now, in order to simplify this entire numerator, we're going to make a common denominator and write this 1 as 5 plus h over 5 plus h so that we can combine it with this fraction. And so combining our numerators, we get 5 plus 2h minus the quantity 5 plus h. It's important to remember to use parentheses here or to distribute that negative sign when you're subtracting. Also notice the denominator we have here of h over 1, dividing by h over 1 is the same as multiplying by 1 over h, so that h can just get multiplied into this denominator. So we continue to simplify in the numerator, and we notice that we're going to be left with just 1h over 5 plus h times h. And again, we can cancel a factor of h. And at this point, we plug in h equals 0, and we get a slope of 1/5. So this is a slope of our tangent line. And so to find the equation of the line, here I'm using point-slope form. Our point is 2, 1, so I have y minus 1 is equal to 1/5 times x minus 2. So that's y is equal to 1/5 x minus 2/5, and then I'm adding this 1 over to that side, and I'm writing it as 5/5. So we have y equals 1/5 x plus 3/5, and that's the equation of our tangent line 2g of x at x equals 2. Find the slope of f of t equals 3 over radical t minus 1 at t equals 5. So again, we're going to start the same way. F prime of 5 is equal to limit as h goes to 0, f of 5 plus h minus f of 5 over h. Plugging in 5 plus h here for t, we have 3 over radical 5 plus h minus 1. Plugging in 5 for t, we have 3 over radical 5 minus 1. All of that over h. So simplifying, this becomes 4 plus h. And this becomes radical 4, which is 2, and so we're here. And we want to make a common denominator to combine this numerator. So we're going to multiply our fraction on the left by 2 over 2, and multiply the 3/2 by radical 4 plus h over radical 4 plus h, and so we're here. So combining our numerators, we have 6 minus 3 times radical 4 plus h. And this denominator is 2 times radical 4 plus h, so we're here. And again, dividing by h over 1 is the same as multiplying by h, so we can write this with the h in the denominator. Now we still have a little bit of work to do to get rid of the radical in the numerator. So we're going to multiply, as we usually do, by the conjugate. So this is going to be 6 plus 3 radical 4 plus h over 6 plus 3 radical 4 plus h. Again, this negative sign becomes a positive, so that when we multiply through in the numerator, the middle terms will cancel, and we'll end up with 36 minus 9 times quantity 4 plus h. And in the denominator, we keep everything factored, and so we're here. Notice that negative 9 times 4 is negative 36, so that cancels with the positive 36, and we're just left with negative 9h in the numerator. Which is great because now we can cancel this h with this h, and then plug in h equals 0. And so we're here, we have negative 9 over 48, or negative 3 over 16. And that's the slope of f of t at t equals 5. Now let's take a look at rates of change. We started the lesson by saying we were looking for the rate of change of y equals f of x, and we have been finding the rate of change of f at x equals a, which we also know is called the slope of f of x at x equals a, also called the slope of the tangent line to f of x at x equals a, and also called f prime of a, the derivative of f at x equals a. And to emphasize that this is the rate of change of f at one point, we call it the instantaneous rate of change. We could also talk about the rate of change of f over an x interval, ab. And this would be the slope of the secant line through the points af of a and bf of b. And so that slope would look like f of b minus f of a over b minus a. And to specify that that's the rate of change over an interval, we call that the average rate of change. So let's take a look at the comparison between instantaneous rate of change and average rate of change for this word problem. Here we have the displacement in meters of a particle moving in a straight line is given by s equals t squared minus 8t plus 18, where t is measured in seconds. They're asking for the average velocity over the time interval 3, 4, and also the instantaneous velocity at t equals 4. Well, the first thing we have to do is make the connection between rate of change and velocity. Keep in mind that velocity is the change in distance over change in time, and so this is the rate of change of a distance function. We're given a displacement or a distance function here, and so average velocity is talking about average rate of change. And instantaneous velocity is talking about instantaneous rate of change. So for the average velocity over the interval 3, 4, we're looking at the slope of the secant line. We're looking at s of 4 minus s of 3 over 4 minus 3. That's the slope of the secant line, and that's -1 in this case. And we should pay attention to the units here. Notice that in the numerator we're subtracting distance values. And in the denominator we're subtracting time values. So this is a -1 meters per second. So this is saying that the distance is decreasing, that negative sign is saying the distance is decreasing by 1 meter per second. That's the average velocity over the time interval 3, 4. But talking about the instantaneous velocity at t equals 4, that's the derivative s prime of 4, and so that's limit as h goes to 0, s of 4 plus h minus s of 4 over h. And so plugging into our formula for s, that gives us 4 plus h squared minus 8 times 4 plus h plus 18 minus s of 4. We're subtracting off this entire quantity. Don't forget to use parentheses there. All of that over h. And so this is the limit as h goes to 0. If we expand here, we get 16 plus 8h plus h squared. Distribute here, we have -32 minus 8h plus 18. And then simplify here, we have -2. And so notice in the numerator, we have a 16 plus an 18, and so that's 34. And then we have a -32 and a -2, so that's -34. We also have an 8h and a -8h, so those cancel, and we're left with just h squared over h. Simplifying a factor of h, we get limit as h goes to 0 of just h, which is 0. So that tells us the instantaneous velocity at t equals 4 is equal to 0. And we said that's the slope of the tangent line at t equals 4. So here we're comparing the slope of the secant line, which is an average rate of change. It's just a slope computation between 2 points on the same function. We're comparing that with the instantaneous rate of change, which requires the limit calculation for the derivative at that point. And let's also talk about the units here. We said that the velocity here is equal to 0 at t equals 4. So that's 0 meters per second. And what we're saying is that at t equals 4, at time equals 4 seconds, the distance of the particle is not changing. So note from the graph that the particle is changing direction at t equals 4, and so it stops to change direction. So the displacement of the particle is decreasing until it's 2 meters away, and then begins to increase and move further away again. So at the time when t equals 4 seconds, the particle is stopped to change direction. And so its velocity is 0 meters per second at that time. And so before we end this lesson, let's just review what we've learned here about the derivative at a point. We have f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a over h. We have an alternate formula for that computation. We can talk about that as limit as x goes to a, f of x minus f of a over x minus a. This gives us the slope of f at x equals a, which is the slope of the tangent line to f at x equals a, also called the derivative of f at x equals a, or the instantaneous rate of change of f at x equals a. So here, in this lesson, we talked about the derivative at a particular point, x equals a. You'll see in the next lesson, we're going to talk about the derivative in general for any x value, and we call that the derivative function, f prime of x. And with this, we'll conclude our lesson on the derivative at a point.